Hello, welcome back. Okay, in the last video we were talking about periodic properties, and the four they're going to focus on in this chapter are atomic radii, ionic radii, ionization energy, and electron affinity. So I'm going to go through at least two of them here. We had talked about atomic radii. I'm just going to review it. Again, the distance from the nucleus, in your book it says outermost orbital, but I think a better way of thinking about it is the outermost electron in that orbital. And we said that atomic radii increases as you move down a group, like we would expect, because you're adding another principal energy level as you go down the table. However, it decreases as you move from left to right when you stay within a period. And we said that's because the quantum energy isn't changing, but what's changing is the number of protons pulling on the electrons. We have more protons, therefore the electrons get pulled in slightly closer to the nucleus. So the atoms actually get smaller, even though you're adding more electrons. And we said that this force of the pull of the nucleus is something called z-effective force. And it has to do with pulling density. So you don't need a lot of protons to create a high z-effective force. Fluorine has the strongest z-effective force, even though it only has 9 protons. But it's exerting that force over a very small area. And francium, which has 87 protons, in the lower left of the periodic corner, or the lower left corner of the periodic table, is actually the weakest pulling nucleus on its outermost electron, because its outermost electron is a 7s1 electron. It's far away from the nucleus. So that pull gets distributed. The second trend they introduce is radii of ions, or ionic radii, and that's the same trend as atomic, except for now you're dealing with ions. So we're just going to diagram it real quick. Again, if we have our little periodic table, and we're diagramming ionic radii, which I, of course, am going to abbreviate IR. As we go down a group, all ions get larger. And as we stay within a period and go from left to right, they get smaller. For the same exact reasons. So as we go down a group, if we're looking at group 1 and we're comparing H plus to Li plus to Na plus to potassium, etc., again, the largest of those four, potassium ion is going to be larger than the sodium ion, which is going to be larger than the lithium ion, which is larger than the hydrogen ion. Again, because as you go down the group, you're adding more quantum energy. So here in hydrogen, we only have a nucleus that's left. So it's going to be small. In lithium, all we have left is a helium core. In sodium, all we have left is a neon core. Potassium, all we have left is an argon core after we remove the outermost electron. So our cores are getting larger because the quantum energy is getting larger. As we go from left to right, however, they do get slightly smaller. So potassium and then calcium, even though calcium has more electrons, calcium doesn't have more electrons, so I'll have to show you the difference here. Potassium is actually larger than calcium, which is larger than scandium, etc. across period 4. Because when you remove these electrons, all you're left with is an argon core. So what's the difference between these three? The difference is potassium only has 19 protons, whereas calcium has 20 protons pulling on that argon core, and scandium has 21 protons pulling on that argon core. So as we go from left to right, z-effective force is increasing, and whatever electrons are left are being pulled in tighter towards the nucleus. So if we were to take a look at these ions in period 3, phosphide compared to sulfide compared to chloride. All right. When we add 3 electrons to phosphorus, that bumps it up to an argon core. Same thing with sulfur, same thing with chlorine. But again, what is the difference? The difference is phosphorus only has 15 protons, sulfur has 16 protons, chlorine has 17 protons. So again, the pulling force is getting stronger as we go from left to right, making whatever electrons are left closer, more attracted to the nucleus and pulled in slightly closer. So the trend for ionic radii is the same as the trend for atomic radii. So they remind you in the reading of what an ion is. It's a charged particle. So to get a negative charge, we're adding electrons. To get a positive charge, we're removing electrons from the neutral atom. And those particles there where we have a positive charge are called cations, and the particles where we have a negative charge are called anions. So another thing that we could take a look at is what's happening when an atom ionizes. Why is it forming a positive or a negative? Well, it's forming a positive and negative, if you saw in the last example, because we're trying to create noble gas cores. So do understand that in chemistry, nature does whatever's easiest. So for potassium, which normally has a configuration of argon core 4s1, well, to get down to a core, we have two choices. We can either remove the 4s1 electron, or we can add in 17 electrons and try to bump that up to a krypton core. It's a lot easier to remove one electron than it is to add 17. So another thing that we can do besides the comparison of groups and periods is we can compare ions to their neutral atoms. If you are creating a positive charge and removing electrons, the ion's going to be smaller than its neutral atom. If you add in extra electrons, then those electrons are going to repel each other. So when you create a negative charge anion, you actually increase the size of that particle. For instance, all right, so let's say again we have potassium, argon core, 4s1 configuration, and now we're going to create the potassium ion by getting rid of an electron. Well, which electron are you going to get rid of? Are you going to get rid of one from the argon core? Or are you going to get rid of the valence shell? Well, the answer is the valence shell, because that's higher in energy, and when it's higher in energy, it's less stable. So we're going to remove that 4s1 electron. So if we were to diagram potassium, we say, all right, here's the nucleus, and we have 19 protons in here. And then we have our argon core, which is another 18 electrons. And then outside of it, in the 4s1 shell, we have our 19th electron. So as soon as we get rid of that 19th electron, now we're back down to an argon core. So the potassium atom is going to be larger than the potassium ion. But the opposite is true for negatively charged particles. For oxygen, for instance, that's going to be a helium core, 2s2, 2p4. Now, to create a noble gas core, we have two choices. We can either get rid of all 6 of the valence electrons, or we can add 2 in. Well, oxygen has a very strong Z effective force, so it's going to add 2 in. And that's going to give us a neon core. So again, if we diagram oxygen, here's our nucleus. Here's our helium core with 2 protons. I'm sorry, there's our nucleus, and then the helium core is 2 electrons around it. And then we have the 4 electrons in the 2p shell. Sorry, we have the helium core, and then we have 6 electrons, I'm sorry, in a 2p and a 2s. My bad. All right, so a total of 8 electrons. Now, if we're going to add 2 electrons, and there's already 6 in the valence shell, these additional electrons are going to repel the 6 that are there. So what we wind up with is this increase in size when we complete the noble gas core. So we would say that oxygen is going to be smaller than oxide. So a couple questions then with ionic radii. We can either compare atoms to their ions, or we can compare ions going down a group, or we can compare ions going across a period. So again, here's my group comparison. Here's my period comparison. And then finally, I can make a comparison in terms of comparing an atom to its ion. Positive ions, negative ions. All right, predicting the oxidation states in terms of periodicity. All right, well, there's two types of elements we're going to look at. We're going to take a look at the main group elements, which are the S block and the P block, and then we're going to take a look at the transition metals. And then I will come back and do the last two trends in the last video. Let's start with the main group elements. Okay, we're going to start with the main group elements. Alright, so let's start with the S block. The S block are going to form positive ions, and we're going to strip down to a noble gas core. So if they were to give you magnesium on the test and say, alright, well, here's magnesium, it has a neon core and a 3s2 configuration, predict the oxidation state and write the configuration for the ion that it forms. Okay, well, for main group elements, what we're doing is we're getting rid of the valence shell. So there's 2 electrons in the valence shell, so magnesium will form a 2+ ion, leaving behind only the neon core. So again, that's easy. Group 1 always forms group 1 due to this fact that we're stripping down to the noble gas core, and group 2 always forms positive 2. All right, let's take a look at the P block elements. Well, group 13 forms a positive 3. We said that at the beginning of the course. Group 14, we said don't worry about it because that has multiple valence and can do a bunch of different charges. But for group 15, it forms a negative 3. Group 16, negative 2. Group 17, negative 1. All right, so suppose we have to justify this. Let's use nitrogen as an example. So nitrogen has a configuration of helium core, 2s2, 2p3. All right, so you have a choice here. To form a nitrogen ion, we can either get rid of all 5 of the valence electrons, or we can complete the p shell by adding 3. So we're going to complete the p shell by adding 3. That's easier. So nitrogen forms a negative 3 charge, and by adding 3 electrons, you've bumped it up to a neon core. So again, what will they ask you to do with the main group elements? Well, the main group elements get the charge that we already talked about in the beginning of the course. You just have to show that what you're doing is you're creating a core. For S1 and S2, we get rid of the valence electrons, and we're left with the core. For groups 15, 16, and 17, we're going to add electrons to complete the shell, and that gives us our new core. Now the transition elements are a little different. We said that the transition elements can do multiple charges. And we're only going to focus on the D block. So a couple notes for you first. Do understand that what I'm teaching you is theoretical. In theory, if we were to try to categorize all of the transition elements, these are the trends that it has. However, the reality of it is we haven't always found all these different multiple oxidation states that I'm about to teach you. For instance, despite the rules I'm about to show you, the only ion we've ever found for zinc is the zinc 2+ ion. And the only ion we've ever found for silver is the silver +1 ion. So again, there's a difference between the theory and the reality here. I'm going to show you the theory. In theory, and I would write all these rules down, transition elements can lose one of their s electrons, which means if they lose one of their s electrons, in theory, all of them can form a +1 charge. Now notice I didn't say the d shell electrons. Even though the d shell electrons are higher in total energy, the atoms actually lose their s shell electrons first because they're higher in quantum energy. So it can form a +1, or you can lose both of those s electrons and form a +2. After that, you can add d shell electrons one at a time until the outer shell is only after the s shell is empty. And finally, if your D configuration goes down, now you can start at a half-filled D, but if it goes down to a half-filled D shell, it won't lose any more electrons at that point. So let me give you an example. Suppose I want you to justify all the oxidation states for cobalt. First of all, cobalt can have a 0 charge. It can be a neutral atom, so we should write that. Cobalt is normally argon 4s2 3d7. So it can have an oxidation state of 0. In theory, could it have an oxidation state of +1? And the answer is, if it did, then the configuration would have to be 4s1 3d7. Why? Because we have to justify losing one electron. Where does that one electron come from? Transition elements lose their s shell electrons first. Alright, so we'll continue on. Could cobalt have a +2 charge? Absolutely. And if it did, where would those 2 electrons come from? Well, again, the 2 electrons would come from the s shell. So now we've lost both of them, leaving behind 3d7. Could cobalt form +3? Sure. But we got to lose 3 electrons. So we're going to lose both of the s electrons. Now we're going to start to lose d electrons. Let's lose one of them and leave behind 6 in the 3d shell. Can cobalt form +4? Yeah, why not? Let's get rid of 4 electrons. We're going to get rid of 2 of them from the s shell, 2 of them from the d shell, and that leaves behind a 3d5. Now, can cobalt form +5? No. I don't know why I'm drawing such an angry face. No, it cannot form a 3d5 because at this point, once you reach 3d5, we're half filled. And we know that half filled shells that are large have stability. So nature's going to fight you on it, and it doesn't happen. Alright, so that gets us through 2 of the 4 trends and how to predict oxidation states. So in the last video, I'm just going to go through the last 2 trends and talk about multiple ionization energies. Thanks.